On this worksheet, we're going to practice a reaction that is called formation of the halohydrin. Here's an example of the reaction. We're taking an alkene. We're reacting a halogen atom with it in the presence of water, and we end up with this molecule here, which is referred to as a halohydrin. A halohydrin has a halogen on a carbon atom that is adjacent to an alcohol or a carbon with an OH group. We're going to begin by proposing a mechanism for the reaction. I'm going to start by drawing the alkene, and we will initially be reacting the alkene with the halogen, the Br2. This is just like the regular halogenation reaction. The lone pair of electrons are going to reach out and grab one of the halogen atoms, and we are going to form an intermediate. This would be, we would call this the Bromonium Intermediate. It's got that bromine ion that is still partially somewhat bonded to both of the carbon atoms in the double bond. So this is kind of weird intermediate with this little triangle guy. And there is a Br minus ion that is produced due to the bromine-bromine bond breaking. Now, if this is just regular halogenation, that bromine ion, that bromide ion will come in and attack one of the carbons of the bromonium intermediate and open up that little weird triangle, and we end up with a halogen. But when we have water present, like we do in this case, so I'm going to write out that water molecule that we have, water is more likely to attack than the bromide ion. So at this point, this bromide ion is not going to do anything else for us in the reaction. The water molecule is more reactive, and that water molecule is going to be the thing that comes in and attacks this little bromonium intermediate. We can see from the example up here that it's attacking at the I'm going to call that carbon number 2 at this position right there. So let's draw the attack in that spot. We're going to be attacking with a lone pair of electrons from the oxygen and then opening up that carbon-bromine bond, and that will give us a molecule that looks like this. And even though it's kind of an awkward bond angle, I'm drawing the water molecule kind of sticking in this up position for now. This isn't the best way to be representing stereochemistry, but this is typically how I do it while I'm in the middle of a mechanism. What I'm trying to do is show like an anti or opposite configuration of the bromine and the water molecule that's been added. It's important that you keep in mind with the mechanism of the reaction that when this little guy comes in, when the water molecule comes in, it's going to be adding itself to one side of that little triangle, and that resulting bromine is going to be on the other side. So one option, like I've drawn it right here, another possibility is that it could come in from the bottom, and we could end up with our water molecule down here and our bromine up here. Either way, in terms of stereochemistry, they're going to be opposite of each other. So what we need to do is clean this molecule up. I'm going to choose to use another water molecule. We've got lots of water molecules present. I'm going to use another water molecule to do the deprotonation here, and that's going to give me, that's going to give me this product like that. Now, this carbon atom is chiral, so we do need to show some stereochemistry on this particular carbon atom. When the water molecule attacks, because it has the option to attack from either position, we want to draw this as either one of the possible enantiomers. So now I'm gonna position that wedge bond in a more normal place. I don't know why I just switched that to bromine. So there's one possible molecule product, and here is the other. So we want to propose an explanation for the location of the OH group. Why is the water molecule attacking at this particular spot? Why doesn't it attack out here? Our theory on this is that the carbon-bromine bond is going to start to break as the water molecule approaches. And if that's an accurate theory, the carbon-bromine bond is going to break. If it starts to break a little bit early, it's going to break at the carbon atom that would be best equipped to handle a resulting carbocation or positive charge. So that carbon-bromine bond, if it's breaking early, is going to break from the more substituted carbon to allow for a more stable carbocation. If it broke this bond first, then we would have a primary carbocation, which is not as stable. So the water molecule is attacking at that particular carbon because the carbon-bromine bond is going to break, start to break before the H2O attacks. I shouldn't necessarily say as. I'm going to say like as the H2O attacks. So we want the bromine to break from the most substituted carbon. It is important to point out that this is not an SN1-like reaction. We don't break that carbon-bromine bond for long enough for a positively charged carbon to result. No carbocation rearrangement takes place. This is more like an SN2 reaction than like an SN1 reaction. It's just that as that water molecule is coming in, these carbon-bromine bonds are getting excited about being able to break and get rid of this weird bonding situation, so they just kind of start to break a little bit early. It's not a completely concerted SN2 type reaction. It's also not like a completely two-step SN1 reaction. What is the relative position of the OH and the Br? They are going to be anti to each other, which doesn't really show up in this particular case because the bromine is on a carbon atom that is not chiral. But if this carbon atom was chiral, we would definitely be showing that. And the reason for that is because the water molecule will attack from a position that is opposite of the bromine. The Br plus in our molecule. So wherever we have that Br plus, the water molecule is going to be coming in on an opposite side of it or away from it. It's not going to be coming in on the same side and resulting in something that looks like this. Could this involve the rearrangement of a carbocation? No. Even though we do have this weird thing where the bond is breaking a little bit in advance, like I said, it's not breaking, it's not completely breaking, and it's not breaking far enough in advance for a carbocation intermediate to actually be formed. So no rearrangement takes place in this reaction.